Okay, so in this video, we're going to talk about solving exponential equations. And we're going to talk about when, in this example, what happens when you can't take, say, the base of 3, right? Because when equations we were solving before had this base and this base were able to be simplified or converted into the same base. Unfortunately, at this point, there is no exponential value for which I can multiply 3 by itself so many times and 4 by itself so many times to get the same number. So the problem with that is going to be is, well, how do we do this problem then? So if these two things can't be turned into one another, okay, what we're going to have to learn to do is we're going to have to learn, all right, to somehow, some way make this no longer an exponential function. So if we have to basically take it out of its exponential form. And to do that, all right, this is where we introduce one of our very first rules that we talk about with logarithms. And one of the very first rules we talk about with logarithms will be this formula. So if you have a formula that has a logarithm, oops, sorry, wrong color there. Okay, so if you have a logarithm, all right, so because to do this problem, remember, logarithms are the inverse operations of exponential equations. So what a logarithm will do is it will allow me, okay, to remove an exponent out of an exponential form. That's the whole purpose of a logarithm. So if you have a logarithm of some base a of some value b, and that value that you're taking the logarithm of has an exponent, the rule, okay, once you took the logarithm of something with an exponent, okay, that's what now is the rule. This is how we undo the exponent. So what happens is it turns the exponent from an exponential value and it turns it into a multiplier. So it bumps it down a level in order of operations. So that exponent now becomes a multiplier of the logarithm of some base a. So the base a is just whatever base you may have of that b. So there's the rule, and that's the rule we're going to use. So now you're going to need a calculator also for these problems, because what's going to happen is you're going to turn this piece into a multiplier, and the logarithm of a number, okay, can be typed in the calculator. We do not want to try to do some of those by hands. We can evaluate them. We did them without a calculator. But for the most part, we really don't want to have to worry about calculating the logarithm. So for the next couple of minutes, you will need a calculator, and I will be grabbing a calculator as well. And the reason I'll be grabbing a calculator is because you don't want to have to solve something by hand. Meaning, okay, that if I asked you to evaluate the logarithm, okay, of say like 7, to do this by hand would be kind of hard because the log, so this is what we call just the log base 10. So if you don't have a number here, it's called log base 10. And remember this when we were evaluating them before, is that this problem would be 7 raised to what power? So remember, we were trying to figure out the exponent, gave me, okay, so the value, joking. Sorry. It was 10, so the base, remember the base. So 10 raised to what power gave me a value of 7, and that would be almost impossible for you to be able to figure out what value of an exponential form, okay, gave you 7. All right, so that would be very, very difficult for you to figure out by hand. So that's why we're going to want to use the calculator for these to help us out through our work. Okay, so I'm going to do this problem. I just want you to understand that we are going to be using logarithms. And again, just to go through that rule, we will take a logarithm of a function, and when you take the logarithm of some exponential function, we will take a logarithm of any base. Now, there's 2 general logarithms we'll talk about. So you have just the general log, okay, which is just log base 10. All right, and then you have the natural log. So I know I haven't talked a whole lot about this, but natural log, okay, the natural log is going to be log base e. But because that kind of looks funny writing it like log base e like that, what we do is we convert that just to the natural log. So you have 2 functions. You have log base 10, which can be just written as log, and then you have the natural log. So those are the two that I predominantly always use when solving equations. You can use either one. It does not matter which one you use. It does not actually matter which logarithm and which base you use to solve any of these, but what does matter is that when you solve equations, what you do to one side, you must do to the other. All right, so whether you use the natural log, which is a logarithm that has base e, which is very important in fields of statistics, it's important in actuaries, so that's why we talk about natural log. And then you have log base 10, okay, and log base 10. Let's think about scientific world, so base 10, you know, talking about all of the scientific notation stuff, okay? So if we go ahead and we move forward here, all right, just to get into this video and get this example taken care of. So these problems do become a little bit more in depth, okay? Because if you take the log of a number, okay, if you just take the log of a number, you will get a number out, yes? So these problems are going to be multifaceted. So what I mean by multifaceted is, first we are going to the step one, right? So if you break this down into steps, step one is going to be to convert, okay, the exponent to a multiplier, okay? So you convert it to a multiplier and you do that through logs, okay? So you do that through logs. The second part to this will be, I'll show you after that, okay? So let's go ahead and do that. So the first thing I'm going to do is I'm going to look at this problem, and I realize that I've got an exponent, okay? But the only reason I'm choosing to use logs, right, is because I noticed that this base and this base cannot be converted into like bases. So what I will do is I will take the log of both sides. So now I'm just going to use log base 10, so log base 10. So I will take the log of this, okay, and I will take the log of this side, okay, and when I take the log of both sides, what that does, that allows me to complete this step one. So what it does is it converts these exponents to become multipliers. Now, you just need to remember when they're written as polynomials that they're groups. So what happens is that exponent, okay, becomes the group of 2x plus 1, and you are going to multiply that by log 3. So that turns into log 3, okay? And that equals, okay, so we go to the other side. So this gets converted into a multiplier. So it's the quantity of x minus 5, okay, times the log of 4. And now from here, what you have is that you have log 3 and you have log 4. So what you kind of have to remember here now is we've done step one. We've done the most part that what we really need to know. And at this part, what I'm going to do to make life a little bit easier for myself, okay, you don't have to, and some people tell you not to, but for the explanation of this video right now, I am going to go ahead and do something that I usually tell people not to do, but it's just when learning to do this, it makes life a little bit easier for you to see what's going on. And here's what it is, okay? Log 3 is a number. So what you now need to know is that if I type in my calculator log 3, and maybe you type it in as well, okay, you're going to get a decimal value, all right? So, and by the commutative property, because it's now a multiplier, what I'm going to do is I'm going to rearrange this so that this decimal is going to be out front. So I'm going to estimate that decimal, and I'm going to say go to the 10,000. Okay, so I'm going to have 0.4771. So that is an estimated number, and then I did the commutative property at the same time because of multiplication. So parentheses, 2x plus 1 equals, and now I'll take the logarithm of 4. So I write log 4 and hit enter, and I'll do the same thing I did there, and I end up getting 0.602 and then 1 by estimating, and then multiplying that by x minus 5. And now what you have, right? So what I did here in step 2, okay, is I'm just going to be converting the log, but that's not really what step 2 really is, because in general, you really shouldn't estimate in a problem. I'm doing it for the explanation piece, and I'll do another problem in which I don't do that, okay? But I will show you what you properly should do. So anyhow, so we're going to go forward here. So the second step is actually, it's an algebra 1 step. So what I mean by an algebra 1 step, it's distributive property. Okay, so we're going to do the distributive property. So we distribute. So 0.477, so 0.4771, we're going to distribute. So now we're just going to do distribute, and times that by 2, and you get 0.95. So estimating here, and usually you really don't want to do this, but we are, 0.9542x plus 0.4771 is equal to 0.6021x, when we distribute. And then I distribute again, so 0.6021 times that by 5, and you get minus 3.0105. Okay, and then from here what you notice is we're just doing literally a linear equation just with a bunch of decimals. So we're going to combine like terms. So I'm going to go ahead and subtract 0.6021x, subtract 0.6021x, and I'm going to subtract 0.4771 from this side, and subtract 0.4771 from that side. And what you get is that side cancels and this side cancels. So if I take that 0.9542 and I subtract this 0.6021, I'll get this 0.3521x, and that's just going to be equal to whatever this one over here makes, so negative 3.0105 minus 0.4771, and you end up getting this negative 3.4876. And the last step here is going to be to divide. So I go ahead and I divide both sides by 0.3521, 0.3521. So divide that by 0.3521. And you get that the final answer is that your x must have a value of negative 9.9051 when estimating. Okay, so now, that may have lost some statistical value when I estimated in the beginning, but the whole purpose of this video really is the part that kids are going to struggle with when they first learn this, is they struggle with the fact that when we leave this in exact form. So what your math teacher loves to do, and I don't necessarily know why, me personally, even as a math teacher, it's just like, okay, it's just something we've always done. But the other reason for it, okay, the why we have to do it, I guess, is the fact that you really should never estimate in the middle of a problem. You should try to leave something as exact as possible. And if you noticed when I typed in the calculator, if you were following along and wrote log 3, okay, 0.4771 was not the exact answer for a logarithm. Okay, I did round it. And when you round in the middle of a problem, depending on what field you're in, if you round inappropriately, you lose some statistical data and it could skew results. So my answer down here of negative 9.9051 is skewed. And we want to try to not skew it until the very, very end to the when we skew it to the decimal value that we properly need. Okay? All right, so that's it. That's how you do these problems. And I'll do one more example here just to kind of go back through it. But I will also this time use the natural log, and I will keep it in exact form. Okay, so we're going to talk about the difference between what I did in the first problem here and leaving something in exact form. So exact form, all right, it's going to recall you're going to need to recall some skills from what is called literal equations. Okay, so literal equations, right? And here's what I'm meaning by literal equations, and what I need you to recall is when solving literal equations, so let's say we had this thing of 2 times the length plus 2 times the width equals perimeter, right? Well, if I told you to solve this for W, okay, you would go through your steps and you would subtract 2L from both sides and you divide by 2, and you're left with a problem that says W equals P minus 2L all divided by 2, and you look at it and you say, what purpose does that serve for me? How does that look any better? It actually looks more complicated because you put fractions in there than it did if I just had it solved for perimeter. And that's kind of the thing that I want you to understand here, is that when you leave these things in exact form, they're going to look more complicated than you would if you were able to just leave them as they were, which is why showing it with decimals is a little bit understand. We're going to go through the same process, but I'm going to have to add a couple of things that are algebraic steps. So just remember that we're going to get problems that are not going to look any nicer than the way they started, and that's okay. When you leave it in an exact form, it is what it is. So let's get into a problem here. So the problem we're going to take a look at is 2 raised to the 3n minus 4, which is equal to 5 to the n plus 1. So for this problem, step 1, it's the same as before. It doesn't change. The only thing I'm going to do now, instead of using log base 10, I'm going to use the natural log, because going through all this work, just having to write 2 letters versus 3 letters is going to make my life a little bit easier. So remember, I'm going to use log base e, which is the same thing as just writing natural log, okay? So I'm going to take the natural log of both sides, so that's how I start off this problem. I take the natural log of this side, I take the natural log of this side. That demotes our exponent to a multiplier, so that becomes 3n minus 4 times the natural log of 2, which is equal to, demoting our exponent, the quantity of n plus 1 times the natural log of 5. So now at this point, remember, so after step 1 was demoting our exponent to a multiplier through logs, was step 2 was distributive property. So now this is where it begins to get mucky, and it begins to not look so nice, all right? So here we go. You know what? For purpose of this video, I'm going to change my n's to x's really quick. Sorry, because if that's a bad one, using natural log. So my variables, I'm going to change to x's. So sorry about that really quick. Okay, so here we go. So now this problem is to distribute. Okay, so we go ahead and do the distributive property. So now we're going to distribute natural log 2 as natural log 2, not as a decimal like we converted last time. So when I go ahead and do that, I take the natural log of 2 times 3x. Now, this is a term with a variable. So there's the way that this would normally be written, I'm just going to show it down up here in blue. Okay, so I'm going to write this up here in blue. The way that this would normally be written as 3x natural log of 2. So that's how people would write it. They usually write the log last in this case, right? For our purposes, what I'm going to do is I'm going to use the commutative property, and I'm going to place this x back here. Now, when I place the x back there, it's important that you know I must use some sort of a grouping symbol. Okay, nothing wrong with what I'm going to do, but by moving this x from out of the front and to the back, I must put a grouping symbol. So that's what I'm going to do. And I'm going to do that because it's a little bit easier to see. I guess I can say it's a little bit, in my mind, a little bit easier to see like terms in the end. So when I distribute this, okay, as opposed to writing it as 3x natural log of 2, I'm going to write this as 3 natural log of 2, and then I'm going to put a bracket as a grouping symbol, x. So I hope that makes sense. And then the next thing I'm going to do is distribute the natural log of 2 to negative 4, so I get negative 4 natural log of 2. And that is equal to, so distributing natural log of 5, so I get natural log of 5, and I'm going to do the same thing like I did before when I have a variable. I'm placing the x here, and then it's plus natural log of 5 when you distribute to positive 1. Okay, so at this point, what I want to point out to you here is that where are my like terms? Okay, so my like terms first, wrong tool. Okay, so my like terms first. My first grouping of like terms is right here. It's natural log, 3 natural log of 2 of x, and then here is its like term, okay? And then my other like term is negative 4 and natural log of 2 plus these, okay? So those are the ones that need to get combined. So that's what I'm going to do now. So I'm going to combine my like terms through properties of equations. Okay, so step one, I'm going to combine them. So I'm going to write plus, let me get an actual pen here. So I'm going to write plus 4 natural log of 2 to both sides, plus 4 natural log of 2 to both sides. And this side will cancel out. And then I'm going to go to the other side, and I'm going to go minus natural log of 5x, okay, and minus natural log of 5x, okay. Now, there's a couple mistakes people will make. They'll start trying to add the numbers here together, and unfortunately, when it comes to natural logs and it deals with exponents, you can't do anything with them. They're not the same. So at this point, I'm going to rewrite this problem with these things gone, and I'm just going to rewrite it again, thinking of this as literal equations, because this is not a natural log of 2 and of that sort. There's literally nothing we can do here, okay? These logs aren't the same, nothing we can do, okay? The logarithm is what dictates whether we can do things or not. So rewriting this becomes 3 natural log of 2 x minus natural log of 5x, okay, equals the natural log of 5 plus 4 natural log of 2. And from here, okay, I have one step. So again, we're in literal equations. So in literal equations, when we're trying to solve for a variable, all right, we need to remember that these here are like terms, okay, but they're separate from one another and they share the same variable, and they share the variable we're trying to solve for. So at this point, if you wanted to consider this step 3, this is combining like terms, so CLT. And then number 4 here, what we're going to have to do is, if we have to, and 99% of the times when you have problems like this, when you have variables on both sides of the exponents, you're going to have to factor the x, okay? So we factor this side, and when we factor it, we factor out that x, and it becomes x in parentheses, so 3 natural log of 2 minus natural log of 5 equals just what the other side is, natural log of 5 plus 4 natural log of 2, and literally last step here is going to be divide. Okay, so when we talked about literal equations in the past, you have to understand we're just going to break apart the operation. So the operation is multiplication, so I must divide this entire side by what leaves x by itself, and that is the quantity of 3n natural log 3 times the natural log of 2 minus the natural log of 5. And over here, I rewrite this as 3 natural log of 2 minus natural log of 5. Now, at this point, I'm done. I have my final answer. There is nothing that can be done here, okay? This is a quantity, and this is a quantity, and much like we talked about before, unless quantities are identical, you cannot, okay, you cannot reduce anything. So don't try to reduce your natural log of 5 because they're both natural logs of 5. They're not. This is natural log. The numerator is natural log of 5 plus 4 natural log of 2. That is one whole factor, okay? And 3 natural log of 2 minus natural log of 5 is one whole factor, okay? You have to combine, you have to reduce factors with other factors. You can't do partial factor with partial factor. It doesn't exist. So this final answer is x equals the natural log of 5 plus 4 natural log of 2 divided by 3 natural log of 2 minus natural log of 5. And like I said to you before, okay, that doesn't look any prettier than what I started with. And that's the idea of having a literal equation, okay? A literal equation is kind of the art of making something solved for, so that if you knew the answer, you could plug it in. But now, okay, if you wanted to, you could type that all in the calculator and you'd get an answer, because these are all just decimals. It's just now I would get exact answers, and then I could round my final thing. So I hope that helps, but there's a problem with exact form versus rounded form. Obviously, the exact form is harder, and this is probably what most teachers want. So that first explanation is kind of like a hope you to understand the process, but this last example is really how the answer should be left. Okay, so I hope that makes sense. Let me know.